everybody. So today we're looking at the first fundamental theorem of calculus, or FTC number 1. Remember that we already looked at the second fundamental theorem of calculus. We kind of went backwards here a little bit. And our second fundamental theorem of calculus basically told us how to take antiderivatives and we defined a definite integral. So just kind of to review, our second fundamental theorem of calculus looked like this. We had an integrand, and we were going from our bounds A to B, and we said the way that we find this or define that area between A and B, we take our antiderivative, we plug in our upper bound, we plug in our lower bound, and we find the difference between the two. And remember that this capital F, that represents our antiderivative. And this is going to come back to us today as we go through our first fundamental theorem of calculus. So just a little bit of a recap. Our second fundamental theorem of calculus is the one that is listed at the very top here. So I'll have you take a moment to write this down. I know it looks intimidating, but we are going to break it down a little bit here today so you can understand a little bit more what that actually means. So let's just play around with it for a little bit. Let's kind of define what this is actually talking about. If I have this integrand listed up there, this is saying that I want to define an area between the bounds a and x of a function t. So a, this is going to be an actual number, but x, we're saying, oh, we're just going to go to some value x, and we're defining it via variable. And our function is in terms of t because we just don't want to keep using x's. So you will see t in this problem, okay? Now let's go about solving this problem like we would normally. So based on our second fundamental theorem of calculus, what we would do is we would find our antiderivative of f of t, and then we would plug in x, we would plug in a, and we would subtract the two. So let's do that. I would find my antiderivative of f of t, and I would plug in our two bounds. So remember, that's our fancy notation. So from here, I'm then going to take my antiderivative of x minus my antiderivative of a, and that would give me this actual defined area. Okay, so let's talk about what this would look like. Obviously, we don't have an actual value for this antiderivative of x. We're dealing with variables here. However, we said that a was an actual number. So when we have an antiderivative and we plug in a number, we're going to get an actual number here. So it could be 2, it could be 10, it could be negative 37, it could, whatever. But it's going to be an actual number here. We're still just going to have variables in that first section. Now let's go back and look at what our first fundamental theorem of calculus is actually saying. If I go back up here, we're not just dealing with this. Our first fundamental theorem says then I want to take the derivative of what I just found. Okay, seems weird, but let's go with it, okay? So going back to where we evaluated, I now want to take the derivative of this. Okay, so let's talk about what that would mean. If I'm taking the derivative of each of these parts individually, so let's start with this capital F of x, our antiderivative of x. We know that derivatives and antiderivatives are opposites of each other. They undo one another, they're inverses. So if I take the derivative of the antiderivative of x, that's just going to completely undo each other. They're going to wash each other out, and we're just going to be left with this function itself. Whoa. Okay, now let's talk about this second part. If we know that our antiderivative of a, that's going to be an actual number, we already talked about that, and if I take the derivative of any constant, you and I both know our derivative of any constant is just 0. So I'm left at the very end, because that 0 is not doing anything, with f of x, which goes back to our rule. We said, hey, if I take the antiderivative between our bounds a to x, then I take the derivative of it, I'm going to be left with that function itself, or f of x. All right, let's go through an actual example because right now it's all kind of theorized and it seems a little bit funky. So let's say we have an example of, we're going from 5 to x of t squared dt. And I want to find the derivative of this with respect to x. Let's deal with what's in our parentheses first. Okay, so we know in our parentheses, when I evaluate this, I'm going to have my antiderivative of the function t, and then I'm going from 5 to x. Sorry, my cat's meowing. So I'm going to still leave this derivative out front. So by definition, with my second fundamental theorem of calculus, I have to plug in the top bound, plug in the bottom bound, and subtract the two. And remember, again, that capital F, that represents our antiderivative. So now, just like we talked about before, now I'm going to be left with this part that will be an actual number, and we're taking the derivative of both. So our derivative of our antiderivative, well, those undo each other. We're just going to be left with f of x minus 0. But let's talk about what f of x actually is. This is the function that we already started with, defined at x. So all we have to do at the very end is plug in x to our original function, and our original function is that t squared. So I'm left with x squared minus 0, or just x squared. And voila, we have used the first fundamental theorem of calculus. So basically, you'll notice as we look at these two, basically what you're doing is replacing the t's with x's. But I wanted to show you why it works the way it works. So once we catch up on that pattern, then you guys can go from there and say, okay, well, everywhere I see a t or everywhere I see whatever variable we're using, I'm just going to plug in an x, and that's my first fundamental theorem. But there is a reason, there's a method to the madness here. So go over this, make sure you have notes over this topic, and we will kind of review it a little bit in class. Thanks, guys.